Hello everyone. In this video we're going to go over the solutions for one-to-one functions and inverse functions. So first let's start with the day one. So before in class we were talking about that a one-to function has the property that if you have an input, that input is just going to go to a single output. And this is one of the most important things that you can determine. So there are many ways of doing this. One of them is going to be graphically. So for example, here we have some examples. We discussed some of this in class before, but I want to stress this out and leave it here in the video so you can come back to it if necessary. So for example, the first one is not a one-to-one function. Similar as the fact that you can do a vertical line test to determine if something is a function by checking if an input has two outputs. With one-to-one functions, you can do a horizontal line test to see if two outputs comes from different inputs. And that's precisely what I'm getting here. Notice with this first function, you can do a vertical horizontal line here, and you're gonna find out that this height, like 0.5, has multiple points that corresponds to that same point. In same way, you can see that this one is not going to be one-to-one because if you do a horizontal line here, then you can see that it touches more than 2 points. The constant function is also a case where it's not because, well, everybody's going to the same output regardless of the input, so it's not going to be one-to-one. The x square or x square family of functions, when you translate x square, is definitely not a one-to-one because you can at least find out that any output has two inputs that are related. This one is also not, but we have a case here where we do have an example of a one-to-one. If you notice, every time that you cross a horizontal line here, there is no one-to-one. There is no 2 points that is touching at the same time. There's no two inputs that are related for each of these points. Now let's go down to the other graphs. Here we have another case of another constant function, and we can see that indeed this is not going to be one-to-one. All the inputs are going to a single output that's not one-to-one. This seems to be a translation of the xq function, and that's a one-to-one. If you do a horizontal line, you notice that each of the heights, each of the elements of the y-axis corresponds to, or is only appearing once, and it corresponds to a single input. This, of course, is not going to be one-to-one. This one here is also not going to be one-to-one because it has, although it's two constants, it has too many values going to the same place. This one is one-to-one. We don't see repeated values, and this one is not a one-to-one. When we do horizontal tests, we notice that it touches more than 2 points. Okay, so that's from the graphical point of view. Now let's see one of those questions that was on the participation from yesterday. And here we're representing the function as a table. So we're asking what can be the value of f of 1 in order for f to be one-to-one. And of course, 1 here was the one that is not written, of course. And so we see that 0 was going to -1, 2 was going to 5, 3 is going to 6, 4 is going to 8, 5 is going to 10. And so those are the options that are taken. So I cannot do 5, 6, 8, that are these options, because otherwise the function will not be one-to-one. -1 is also taken because 0 is going to -1. So the only option from the multiple selection is going to be 2. And that's pretty much the result that we can do here. Now there are some other values that I cannot take that are not here. For example, -10 cannot be. And there's a bunch of other different values that one can take. For example, 1 could be 3, 1 could be 50. It could be many values, but because we're selecting for a specific list, that's the value that we can get. Now, question number 4 is about, is the function x minus 1 squared not one-to-one? We kind of spoke about this yesterday in class. X minus 1 squared is just a translation to 1 of the x squared. And so we notice that we're still when we do that horizontal line test, we still get 2 points at the same height, and that means that we have one output that is coming from 2 different inputs. And so that's not a one-to-one relationship. Now, in question number 5, we have this same type of evaluation, but with multiple functions. We have first the line, and as we've discussed, lines are actually one-to-one because it matches one input to one output. Here we have a more complex version of the quadratic that of course is not going to be one-to-one in minus infinity infinity. So we're covering the whole minus infinity to infinity. It's not going to cover it, but we can find restrictions on their domains to make it one-to-one. So notice that if we only take 1 to infinity, then this function will be one-to-one because we are essentially erasing the repetition. So if we're only considering from 1 onward to infinity, we're only considering the right side of the parabola, and that's going to make it so it's only one-to-one. Similarly with the absolute value. The absolute value of x minus 2 is in general not one-to-one in minus infinity to infinity because of course this is like moving the absolute value to 2. Alright, and so to the left of 2 we're going to have the same values that to the right of 2. So that means that if we just consider from 2 to infinity, we're just gonna get the distance once, not twice like we're normally doing here. And so that will just make this one-to-one. So we definitely don't have one-to-one in everything, but we can restrict it so it's one-to-one in certain pieces. Now the 1 over x, it is one-to-one in everything but 0, because notice that 1 over x cannot be defined in 0. So here, notice here's taking negative values, here's taking positive values. So this is one-to-one in all minus infinity, infinity, but 0. So we remove the 0 from the domain. Now 1 over x squared is a similar situation, which it cannot take 0. However, this is not going to be one-to-one in minus infinity, infinity, because this is, regardless if we're taking negatives or positives, it's still giving me the same values to the left or to the right of 0. So we just need to keep one of those. If we want to keep it to be one-to-one, we can keep either the left side or the right side. So we can, for example, r of x here is going to be one-to-one if we just restrict this to the 0 infinity domain with 0 open. Or we can also restrict from minus infinity to 0, and that will make it one-to-one. Now for question 6, we have the function x squared and x cubed. And for a function to have an inverse, it must be one-to-one, of course. And so we want to know which of these functions has an inverse and what is its inverse function. So on minus infinity to infinity, f of x equals x squared is not one-to-one. So it's not going to have an inverse in minus infinity to infinity. We can only we restrict, then we're going to have we can have one-to-one, but since we're not talking about restricting here, then in general it's not going to have an inverse. X cubed is one-to-one in minus infinity to infinity, as we saw from the graph. And if we switch, the way that we do this is, remember, we're changing the input for the output. So we can, to find the function, we can just start by switching x and y. And so y equals x cubed is now going to become x equals y cubed. And so once that I set up that way, I'm going to solve for y. And so what happens is I'm going to take cube root on both sides. And so that's going to give me that y is cube root of x. And so my new inverse function is going to be cube root of x. Okay. Notice that this is a more organic way of changing input by output. So I encourage you to follow this way of finding the inverse. First, switch it up on the variables, change the input by the output, and then solve for y. Let's do the same thing for now phi x minus 2. Phi x minus 2, we know that it's a line, so it's a one-to-one function. First, we're going to take y equals phi x minus 2, and we're going to switch x and y. And so that's going to transform into x is equals 5y minus 2. But then that means that if we solve for y, then we're going to have that x plus 2 is 5y, and then x plus 2 over 5 is y. So f minus 1 of x is going to end up being x plus 2 divided by 5. Now this type of line, notice that it transforms into another line on the inverse, so it kind of makes sense to what we saw graphically. Now finally, for exercise 8, we have the root of x plus 1 minus 5. Of course, this has to have a domain where x is bigger than minus 1, so it can exist. And so we want to find the inverse. Here it's important to notice that we have the domain x bigger than minus 1, so we know that it's well defined. So first we set y equals square root of x plus 1 minus 5, and then we're going to switch the x and y variables, so we're switching input and output. And so now we have x is equals to square root of y plus 1 minus 5, and now we're going to solve for y. So we take x plus 5 is equals to square root of y plus 1, then we square on both sides of this equation, and then we're gonna get that y is x plus 5 squared minus 1. And so my new function, my new inverse function h minus 1 is gonna be x plus 5 squared minus 1. Alright, so now let's see a little bit of the composition. So we have g of x equals 3x plus 5, and then g minus 1 of x. The inverse of this function is going to be x minus 5 over 3. When we compute g compose g minus 1, we're going to find out this very particular property of the function in the inverse. And is that when we compose either g with g minus 1 or g minus 1 with g, we're going to reach something that is called x, or is called the identity function. Okay? So we saw composition before. G composed on g minus 1 is plug in x minus 5 over 3 on the function g, and so that will be 3 times x minus 5 over 3 plus 5, so that's going to lead to x minus 5 plus 5, and that's going to lead to x. And notice if you do it the other way around, same thing is going to happen. Okay, so here just to make the small clarification, if we do g minus 1 compose g of x, this is g minus 1 composing g. And so remember what g minus 1 is x minus 5 over 3. So this is g of x minus 5 over 3. And then this will be 3x plus 5 minus 5 over 3. And then 3x plus 5 minus 5, the 5 cancel out. We have 3x over 3, and then that's going to lead me to x. So a function composed with its inverse is always going to lead me to x. So that makes it like a good way of proving that something is an inverse. Now for exercise number 10, we have f of x being square root of 5 minus x, and we want to find out what f minus 1 of 2 is. And so there are two ways that we can solve this. First is we find f minus 1 of x and plug in 2, or if we know that f minus 1 of 2 is certain number x, then that means that f of x gotta be 2. And so that means that the square root of 5 minus x is supposed to be 2. So therefore, a square root of 5 minus x squared is 4. And so that means 5 minus x is 4, or x is equals 1. So that kind of is something that we can confirm by plugging and seeing that f of 1 is going to be square root of 5 minus 1, which is 2. So, indeed, f minus 1 of 2 is going to be 1. Remember, there's this dual relationship between things. Don't forget about that relationship, because it's super important. If y is equals f of x, then remember then x is f minus 1 of y. This is a dual relationship. So if I say 2 is f of 1, then this is equivalent to say, hey, f minus 1 of 2 is 1. All right? Okay, and so with that, I'm going to conclude the solutions to the day 1. In the next video, I'm going to go over the solutions for day 2.